A warm good evening, everyone. It's a great Sunday today. It's the fourth day of the International E-Conclave. Very interesting day because on the last 4 days we have been, since the last 3 days we have been speaking about a lot of things about pharmacotherapy related to tobacco cessation. So today we have the consensus whereby all the moderators from the last three sessions are going to present a short summary, and then we are going to have a great panel discussion with the topmost surgeons from different specialties across the country session. So now with this, let us move ahead, and I take this privilege now to invite Professor Dr. Rakesh Rawal from Gujarat University. Sir is professor from Life Sciences Department of Gujarat University and is also a coordinator for the programs, academic programs at ICanCaRe. He's from the Department of Biochemistry and Forensic Science, Gujarat University. He has had more than 116 national and international publications to his name on cancer and research. So now he's going to have a short talk on the new research to personalized intervention for tobacco cessation. I invite Sir for his talk.
Good evening, one and all. On behalf of Gujarat University and on behalf of our Vice Chancellor, I am very much thankful to all the dignitaries who are present today for today's event, as well as those who actively participated for making this event successful, and to the whole organizing committee of the E-Conclave and all the participants who are attending this event on this Sunday evening. I am told to stick to the genetic aspect of tobacco metabolism, addiction, and de-addiction. I think in these 3 days, you have a lot of brainstorming and exposure to majority of the portions that was summarized just now, that you have been exposed to the ill effect of tobacco and what are the different therapeutic options available, like NRT and pharmacotherapy. Now, the challenge is, in spite of following all the protocols given by the manufacturer, do we get response in all? So in that case, possibly the answer will be no. And let's quickly go through that part. So before going to expose you to the whole genetic aspect of nicotine metabolism, addiction, de-addiction, let me quickly take you through what are the basic understanding of the genomics and the genetics. So we all know that human body is very complex, made up of organ, tissue, cell, nucleus, as we go down till the gene. So around 50,000 genes have now been reported, and that the genes, they contain both introns and exons as a part of those genes. And ultimately, the whole genome of a human being that contains around 3.2 billion letters of ATGC. They are in the form of a long bead or string. Right? And we have from those complex nucleotide, we get the expression of the various proteins. And ultimately, these protein, lipids, carbohydrate, and nucleic acid, they form the whole macromolecular inventory of human being. And all these genetic makeup, or when we wish to characterize the genetic composition of a cell, usually we take the help of cytogenetics, which is a classical way of representing chromosomes in an ordered form, where we can numerically and structurally look at those chromosomes and look at the anomalies. And later on, we move to FISH, that is fluorescence in situ hybridization, where we see, or where we can characterize the small translocations or amplification of the whole chromosomes. That is the numerical anomalies, aneuploidies. And later on, with the help of molecular genetics, possibly now we can characterize even smaller portion of those genetic changes by using microarray and next generation sequencing. So these are right now in the center stage. But as from a layman's perspective, if we look at, say, normal architecture of a gene, it is the code of ATGC, which are arranged in a linear form. And each 3 nucleotide in the exon, they contribute to a specific amino acids, right? And during the course of replication or during the course of its exposure to various carcinogens, whether it is chemical, or physical, or biological agents, there are chances that we may get some either addition of small bases, or there is a mutation where one base is replaced by some other nucleotide, and we code for a different amino acids, and that's how we get a new mutant. Or a portion of our genome is lost, right? So that is deletion. So usually these are the 3-4 words that we come across when you read a scientific paper on genetics of either tobacco or addiction or say cancer. Insertion, mutation, deletion, right, or amplification. But the ultimate aim is to see whether there was a loss of function of the gene or it was a gain of function of the gene after this insertion, mutation, or deletion. And based on that, the whole prediction of the genetic function is based on. So if you look at the molecular genetics of nicotine metabolism, right? So here, the major part of nicotine is metabolized. So I think around 75% of nicotine is metabolized into cotinine, and this cotinine is further metabolized or biotransformed into various derivatives, that is glucuronide form of cotinine or the hydroxylated form of cotinine, and ultimately these are eliminated out of the body through the excretory system for elimination. Part of that will go to the central nervous system, and it may affect the various receptors over there. Can be the opioid receptors, or it can be the glutamate receptors, or N-acetylcholine receptors, or this can be the dopaminergic receptors. And ultimately, all these are coded by the genes, which ultimately forms those proteins, because all these receptors are proteins. And the biotransformation of nicotine, that also involves several enzymes, right? So if you look at the genes which are involved, or the proteins which are involved for the metabolism of nicotine, I think the major part is contributed by cytochrome P450. So here, the cytochrome P450, 2A6 and 2B6, these are the two isoforms which contribute to the conversion of nicotine to further modifications. And based on the genetic polymorphism, or based on the sequence of CYP2A6, they can be classified into a normal metabolizer, a low metabolizer, or a poor metabolizer. Right? And we will look into the much detail into that. And so when we look at the sequence, or the sequence of that particular gene, and there are several isoforms. So these isoforms are produced because of the alignment of selected exons, and you will have more than one isoforms. So for CYP2A6, possibly there are around 30 different isoforms. And ultimately, the CYP2A6 followed by star and a number. So that shows that the 31 isoforms are available for CYP2A6. And besides cytochrome P450, it is aldehyde oxidase, that is AOX1, and UDP glucuronosyl transferase, that is UGT. So UGT 2B10 and UGT 2B7. These are associated with the glucuronidation of either nicotine or cotinine. And once they are converted into the respective glucuronide, they can be easily, they are now water soluble, and they can easily go out of the body. And there is one flavin containing monooxygenase, FMO3. So that is also associated with oxidation of the nicotine. Ultimately, the metabolism of nicotine, if we look at from a pharmaceutical perspective, then we have pharmacokinetics and pharmacodynamics of the nicotine. So kinetics is what the body does to the substance. So here, the nicotine. And there are reports that if from a smoke, once it is inhaled, it reaches to brain within 10-15 seconds. And then later on, it gets metabolized into cotinine. So the body degrades the nicotine, and the rate at which it is being degraded into its biotransformed or degradation product, it is variable based on the person's genetic makeup. So it is reported that around 60% of the variability in nicotine metabolism is attributed to the several genetic factors. And this complex slide is a pictorial representation of various enzymes which we just listed now in liver, and that is the primary organ where all major biotransformation of nicotine, cotinine takes place, and the soluble form of the degradation products are prepared and they are eliminated. The pharmacodynamics is what the substance does to the body. So once the nicotine or the cotinine or the degradation product, whenever they are getting circulated in the body, what they do to the body. So nicotine will go and bind to its receptor, NACHR receptor, so nicotinic acetylcholine receptor. And ultimately, it will lead to release of adrenaline or release of dopamine, glutamate, epinephrine. That part you have already discussed in depth. Now, if you look at the cytochrome P452A6, that is the most common form of the cytochrome P450 family that is involved in nicotine metabolism. And but if you wish to classify the patient, because if you observe the population, there are few people who hardly require 1 or 2 cigarettes a day, and there are people who are like engine, right? So they are smoking, chain smokers. So why it is so? Because the genetic makeup is so that a normal metabolizer is that in which both the alleles. So if you look at the chromosomal architecture of a cell, we have 22 pair of autosome and 1 pair of sex chromosome. And therefore, each gene is having a pair of allele, one inherited from father and one from mother. So when both the allele are normal, that means 2A6*1A, so it is a full functional allele. And when both the allele are intact and normal, so they will have a normal metabolizing potential. So we call it as the normal metabolizer. However, a low metabolizer is that in which at least one of the allele out of the two is they have lost their function. So here, *9A, *12, all these are falling under the low metabolizer category. And the poor metabolizer is that in which both the allele, they have lost the function, and or they are deleted, or there is some mutation, and that leads to inactivation or loss of activity. So *2 and *4A, they fall into that category, and they are poor metabolizers. So here is a list of all the CYP2A6 isoforms with their functional activity in vivo, and based on that, they can be classified. Similarly, the second isoform, that is CYP2B6, is responsible for bupropion metabolism. So whenever you give bupropion to an individual, and this prodrug will be converted into the active drug after the biotransformation. But if there is an induction of the CYP2B6, then that will lead to increased metabolism, and you will be having available active drug in the system. But if there is some mutation or there is loss of activity, then this prodrug will not be able to getting activated, and possibly that will remain in circulation, and that may cause failure in the treatment, or it may cause toxicity. So CYP2A6 allele *2, *4, *9, and 12 are associated with lower 3-hydroxycotinine to cotinine ratio. That means they are classified as slower metabolizer. So how we can see that? So once you analyze the 3-hydroxycotinine versus cotinine, total cotinine ratio, and that can be measured through HPLC from serum, and that will tell you that if there is low ratio, they are slower metabolized. And based on that, possibly you can design your pharmacotherapy, because if the person is a rapid metabolizer and if we are giving the standard dose, possibly the drug is metabolized fast and it is unable to act on the target with the right purpose. So genes which are responsible for tobacco metabolism, so they are classified into central candidate genes, and that includes the nicotinic acetylcholine receptor. And if you look at the molecular form, they are made up of 5 subunits, and these are either homomeric or heteromeric form. That means there are a combination of alpha and beta subunits, and based on that, so as we discussed, that is alpha 4 beta 2, that is one of the major subunit of the receptor, and hundreds of mutations are reported in these alpha and beta subunits, and ultimately these mutations will lead to formation of a deformed receptor, and that will lead to either an ineffective binding between the drug and the receptor, and possibly that can be the reason that in spite of giving the full dose or the desired dose, we are unable to achieve the desired response. So beside NACHR, there are dopamine D2 receptor, and then dopamine transporters, opioid receptor, MAO, monoamine oxidase receptor, and tryptophan hydroxylase, aldehyde dehydrogenase, GABA. All these receptor polymorphism have been reported, and the specific mutation which leads to either complete loss of activity or partial loss of activity is also reported. So based on the genetics of tobacco metabolism, we can classify into rapid metabolizer or poor metabolizer. So if we can classify them prior to initiation of our pharmacotherapy, it will definitely give us an advantage. So rapid metabolizers are usually chronic smokers, and they respond more poorly to nicotine replacement therapy. However, they are a more excellent candidate for non-nicotine therapy, such as bupropion. Whereas a poor metabolizer who is having either null or reduced activity of CYP2A6, and they smoke fewer cigarettes per day, are less dependent on nicotine, and hence they have an easier time for quitting smoking with simple NRT or even with simple counseling. So once we know the target group, it will be easier for us to decide. Bupropion is a weak inhibitor of dopamine and norepinephrine reuptake. I think that you have already discussed about all the pharmacotherapy, so I'm not going into the detail of that. Similarly, varenicline is a partial agonist. And however, their action is dependent on the cytochrome P452A6 and 2B6. So if we know what mutations they have or what isoforms they have, possibly we can design their recipe more appropriately. So I think that was the part of my presentation. And since we worked a lot on tobacco-related cancer, I was part of the Gujarat Cancer and Research Institute research team, where Dr. Pawan was working as an oncosurgeon. So we did a lot of work on tobacco-related cancers. So during that period, what we saw is that not all smokers develop cancer, right? That means, so that attempt to hypothesize that the genetic factor may render some smokers more susceptible to cancer. So we did a lot of genetic studies in various tobacco-related cancers. And what we found that there is a genetic variation in xenobiotic metabolism, DNA damage repair, cell cycle control, apoptosis, telomere length, MMPs, and these are very specific for specific type of cancer. Even there is a difference in the genetic landscaping of tongue cancer and buccal mucosa cancer. So the take-home message for today's talk is the current smoking cessation treatment are inadequate as the long-term abstinence rate are poor because there is a genetic variation in the target population to which we are treating. And the genetic information can lead to new treatments by identifying novel drug target based on certain natural pharmacogenetic advantages in the cessation. And it can also lead to improvement in current treatment by enabling individualized therapy for the target group based on their genetic background. So looking at all the previous data, we can say that majority of genetic information are currently available from the Western population because a lot of work has been done there. And we have hardly any data from Indian patients. So it is the need to create our own allele variant archive through collaborative approach. And that's how we are in close collaboration with ICanCaRe. And those who are joining ICanCaRe for various courses or as a tobacco cessation specialist, they are part of our network team. And by the help of the whole network, possibly we can generate our own allelic archive. And that may be useful for deciding an effective cessation therapy or protocol for our patient. Thank you.
Thank you so much, sir. I think that was a great presentation, and I'm sure there'll be a lot of questions. So, but we'll not take it now. I'll request the participants to please post the questions on the chat